Hi everyone, my name is Alisia and today I'm presenting Transfomers to you. So we've seen this slide before. It was presented by Michael yesterday. This is the zoo of models of deep learning. And between yesterday and today, we've seen most of them. So we've seen lecture 3, CNNs, also RNNs. Lecture 4, we've seen deep sets, and lecture 5 and 6, and maybe even like earlier today, GNNs. Today I'm presenting the last animal of the zoo. So we're doing Transfomers. I will cover 2 main topics, but it might be a little bit dense. So I inserted breaks. During these breaks, you can ask me questions. So first step is the Transfomers architecture, and second topic is Transfomers as GNNs. There are some references here, some papers that I'm referring to. If you want more details, please do check them out. These are really good papers. Okay, let's start. So a little bit of background. We're talking about Transfomers, and Transfomers are fairly new. And I think it's good to try to understand what was there before Transfomers. So before Transfomers, we had RNNs. And those were the state of the art in NLP for next token prediction, which is like the main task that Transfomers are solving. So in 2016, these were the models that people were using. And I will not go in deep into them, but what is important for us to understand for the sake of this discussion is that RNNs are basically representing the hidden state of the input into one single vector. So all of the input gets squashed, embedded into this final vector of a fixed side HT. Now, RNNs suffer from 3 main problems. One is the sequential bottleneck. So the prediction and decoding of the RNN goes sequentially. And because of that, if we want to encode a later input, we have to first encode or even decode all the previous input. Another problem is the vanishing gradient. So because of this sequentiality, if one of the norms of the Jacobian is it's less than 1, for example, then this leads the gradient to go to 0, or another thing that can happen is the gradient will explode. Last problem that we have is that because of the information, irrespectively of the contribution in time gets squashed to this final state, HT, the information is all compressed. So we lose, basically, the more in time we go through, so the later we are in our sequence that we want to encode or decode, the more information, more context we lose about the initial part of our input. Okay, now, in 2014, let's say a method was proposed. This method extends RNNs from single vector to having many vectors for each specific input. And this is important because this attention and some kind of intuition behind the RNNs will be merged later when we talk about Transfomers. So this was all the background we're looking at. Now let's talk about this. This is a transformer, if people haven't seen it before, and is the architecture that is behind the most used and the most impactful AI applications today, which are LLMs. Okay, just to give you some kind of like visual quantification of what we said before. So RNNs go sequentially. So if I have let's say that my sentence is, he ate the pie happily, then we will need to decode each single token before we can get to the end of the encoding. While what is really cool and makes Transfomers extremely powerful is the fact that by leveraging attention and parallelism, we can attend to all the words in the sentence at the same time. So while an RNN is sequential, so here you can see just a stream, you can imagine like the kind of graph of attention of a transformer as a complete graph. Okay, now let's talk about why a transformer is cool. Okay, so quick recap about what we said so far. So if we look at literally what we said 3 minutes ago, if we look at RNN models, they're sequential transformers going parallel because of attention heads. Memory in RNNs fades over log distances, and this is what we have been talking about before when we were talking about the gradient vanishing, while in transformers is perfect. And here perfect means that in the limitations of the context window of the transformer attends to all the other inputs. Training speed for RNNs is low, transformer is extremely fast, scaling in RNNs is hard to scale. For transformers, transformer is a highly scalable architecture, but the training is not as easily scalable, and we'll talk about this later. Order is inherent for RNNs because, as we said, the processing of the input is dictated by the order of these tokens, while for transformers, this goes away because we are taking all the inputs at the same time. This is later imbued back into the transformers by leveraging positional encodings, which we will talk about later. Gradient stays stable in the transformers thanks to the add and norm and feed-forward layers. And computation for RNNs is linear, while for transformers is quadratic, which used to be a little bit of a bottleneck in transformers, but the novelties that have been introduced architecturally, especially like 2 or 3 years ago, made it not such a big problem anymore. Okay, quick break for questions. Any questions so far? All clear? All right, okay. Let's dive deeper into the architecture then. Okay, so I want to touch on the 2 main novelties that have been introduced by the Transformers paper, which is attention is all you need. One is how do we process the input before using it into our architecture, and the second one is the multi-head self-attention mechanism. So before transformers, usually all NLP approaches had relied on a predefined embedding for the sentences, and transformers instead is learning this embedding, which is super cool, quite revolutionary, especially if given the historical context. So our input X, which you can think about as a sentence, is the combination of 2 parts. First part is the embedding of this word, and the second part is the positional encoding. So if you remember, I just told you now that this embedding is learned at training time. So at the beginning, it's just assigned random vector of a certain size. And then through training, we learn the embedding both for the input and the output of this specific token, or word, if you will. And this creates a lookup table, basically, which is shared between the input and output of the encoder and decoder. And then the second part is the positional encoding. So we've said that transformer is attending to all of these words at the same time, right? And because of that, it's losing the ordering, which is natural in an RNN. Now, this ordering can be pushed back into the model by leveraging positional encoding. So positional encoding is just a sinusoidal function, and this function basically assigns a fingerprint to each input that we have, and is calculated by leveraging the position that this input had in the original sequence over this constant. There's a reason for this constant. If you're interested, we can talk about it during the practical. And basically, it outputs out a number between -1 and 1. And this, you can think about it as a little bit of inductive bias, if you will, a little bit of structure that we are reconstructing into the architecture. Okay. Now, we've talked about how to process the input. Now let's see what we do with this input, right? So in training of the transformer, we learned 2 things. We learned these embeddings for the input and output representations, but we also learned these matrices W, which are called learnable weights. Sorry. And these matrices are initially initialized and random, and the values in these weights change in training. Now, we have 3 of them because they are used to represent 3 different, if you will, flavors that a token can have, like a word can have in a sentence. So number 1 is the query matrix. And the query matrix, you can think about it as some kind of indexing, in a sense. So it's telling you which word in the current context we are interested in using to bias the attention for the others. Then there is a key matrix. This key matrix is a syntactic tag. So it will tell you basically what kind of syntactic relation we want to focus on for this specific word. So for example, if we think about the sentence, I don't know, the dog barks, and the token or word that we're looking at is dog. Dog is clearly a noun, but it's also a subject in this sentence, right? And depending on which word I'm considering, so the dog barks, if we consider the verb, then the noun has a different flavor because the noun is basically like in this case would be like the subject would be the actor of this verb, right? So the key matrix is basically taking into consideration all of these different nuances. And then the value matrix should represent the semantic tag. So what is a dog? A dog is an animal, right? So we kind of want to imbue this kind of meaning into the value matrix. Okay, so what are we learning? We're learning these matrices W's and these embedding X in training. Cool. Okay, now, how do we learn them and what do we do? We use attention, and attention is a score that is computed on these matrices that we have been talking about. Now, let's break it down together. So this is the formula. What we do is basically we, first of all, compute a similarity score. So we're basically asking how similar, how related these 2 words are that I'm considering, right? It's not 2 words, it's basically like between all the words, but just for like sake of, I think, simplification in explaining, let's just say 2 words, okay. Then we scale them on the number of, on the length of that embedding that we are using for the input. So we're basically like scaling it back to our input size. And then we take the softmax. And the softmax is basically like looking at all of these scores and deciding which word should we put most focus on. And then by multiplicating the softmax score with the value matrix, we are rescaling this whole thing. Sorry, we have computed so far in step 1.3 some kind of epsilon, basically a scoring, like a rescaling parameter. And then with V, we're by multiplying by V, what we're saying is, okay, how much should the semantic value of this specific token impact my predictions in the end? Okay, all of these was, so far, all that I have presented, I've been talking about only one set of these Q, K, and V matrices, right? In reality, what happens is that we don't have only one, but we have many. And every set of these 3 matrices is called an attention head. And by having many of them, this makes the inference, but also training faster and more expressive. Because if you have many different heads that attend like to the same sentence, in this sentence, you can choose to encode the different flavor of the sentence, right? So back to what we were saying before, we may put more attention on the verb, more attention on an adjective or certain things, and then in the end, by combining all of these, we don't lose this kind of expressiveness. Okay, just to recap everything we've seen so far. So we have some kind of input. This input goes into the encoder. This input is then multiplied by our weight matrices and gives us the key, query, and value matrices. Then key and query are multiplied into the similarity matrix. So basically, this one in pink. Then softmax, we have cross-attention. Cross-attention is multiplied by the values. We have the indent states. And if you want to go, you just go back. OK, so basically, all of these is this. Now, the difference is here we're having a matrix look at transformer. And here, these are the actual layers. So I just wanted to quickly touch on this figure. So we've spoken about the multi-head attention. We've spoken about the input and output embeddings. And we know like the positional encoding as well. And we've also spoken, and that's everything that we've touched. Now let's see what are the stuff that I haven't talked about yet. Really quickly. So the add and norm layer basically acts as a stabilizer for training. So at the beginning, there's like the dynamic is not really stable. There's a lot of fluctuations. And we add back the input layer to train the model to just pay attention to the residual differences between one stage and the other. In the norm layer, what we do is we rescale activations to avoid nullifying the gradient, which, if you remember, was the big problem, one of the big problems for RNNs. In the feed-forward network, we add a nonlinearity to avoid this collapse of all these like linear projections that we have with the matrices. And then this is like all the layers I haven't spoken about yet. Now, one question that you might have is, why is this thing all connected, right? I mean, to me, at least, when I saw it for the first time, it was really weird. Like, why are all these arrows? And this is called weight tying, and it's done for two reasons. One, it creates a shared semantic space for input-output. So at the beginning, if you remember, I told you that there's embeddings for words are being learned. But if these were not all connected, we might end up having two different representations for the same word in input and output, which is just inefficient, and we want consistency there. And then the second point of why we do weight tying is to just improve efficiency and performance, because it reduces drastically the number of training parameters. OK, now something that I find super cool. Let me check time. OK, we're good. Limitations of this thing, right? So we've said that transformers are the backbone of the most impactful AI technologies that both experts and the broader public are using. What are the limitations? There's plenty of them. And I think it is nothing short of extraordinary how, as a community, we've learned to overcome this and create this like seemingly or powerful, but in reality not, LLMs. OK, so let's look at them. So it's quadratic in complexity, which means that it's expensive. OK, this is not nice. There's a fixed context window. I haven't spoken about it because it's not in this paper, but in the later developments of transformers, basically people add a plus m factor here. This matrix is called the attention mask, and that decides what are the tokens that you're attending to. For a causal transformer like GPT-based is usually like it's autoregressive, so it's everything up to that specific token. There's a lack of inductive bias, which generates a need for high quantity of data. Also the tokenization, so the fact that we take a word, we split it, and we might lose like semantic meaning there, plus the attention mechanism that just attends to all the stuff at the same time, makes it so that it's not really good for what is called system 2 thinking. You can think about system 2 thinking, sorry for the use of thinking, as any kind of reasoning that partakes to science, maths, and logic. OK, now but if we look at LLMs today, LLMs can do maths, right? LLMs then are quite fast, and the context window is something that is steadily increasing. So how are we overcoming this? So quadratic complexity, there's a lot of very cool, very complex architectural work. First of all, LoRa, then some KV cache optimization. We have pushed this to a very optimized state, but still is a little bit of a problem. So if you're wondering what kind of research can I do that is not going to require me a lot of compute, this is great. Great academic research. Makes you cry a little bit, probably. The fixed context window. So if you remember, like 2-3 years ago, when we were using ChatGPT, we were only allowed a certain space in that message, right? That's the context window. And it's steadily increasing. So now you can feed entire PDFs to your to like Gemini or GPT-5. So how do you do this? There's different ways. Some people like to modify attention to increase the length of the attention matrix that we're using. Some people use sliding windows. Some people just re-add the context back into RAG, so they do some kind of summarization, then add it back. This is, again, some kind of research that you can do easily without loads of compute, if you're interested. Lack of inductive bias is solved by annotations. So if we need a lot of data, we just pay people to annotate the data. This is not interesting research, but you maybe want to be interested into doing data augmentation for this problem. Then struggles with maths and reasoning. There's a lot of things that you can use. So chain of thought can be one thing. So you add extra computation time, which makes it so that the transformer uses its layers to do the computation that it was not able to do because of attention. Tool use, so you just train your LLM to call an external network, like a calculator, for example, or RL also works. And in RL, it just learns to basically memorize the answer. Okay, quick break for questions. Any questions? No? Okay, that's lovely. Okay, yes, sorry.
Can you go a little bit deeper on how flash attention solves context?
Can we do that in the practical today? Cool. I'm just saying that because I'm actually going to present these rope and all of this kind of stuff today, so we can do that. Okay, let's look at the last stuff. So now you're aware of what a transformer is. I'm telling you something. Transformers are GNNs. How can we, and this might be like a new statement for some people. For me, it was, and I found it really cool, so I thought that presenting it would be nice to you as well. So a transformer can be seen as a graph neural network where the graph is fully connected and the edges are dynamic, so due to attention. Now, how does this happen? Let's try to find an intuition behind this. So we've seen this in the practical and maybe in the slides earlier or yesterday maybe. And we were focusing the practical on this, so the message passing neural network. Okay. We've also seen the MPNN doing the lectures. And these are the update, aggregate, and message that we combine to create the new hidden state, right? Now, in a GAT, which is like a particular type of GNN, there is a way of basically adding a coefficient that scales the impact of the neighborhood in the aggregation of the message. And you might ask, okay, now that I have this coefficient, and I'm attending in different way to my different neighbors. Is this a transformer? No. So to make, so what is missing between GAT and transformer? So to make a MPNN a transformer, what we need to do is two things. One, make the graph fully connected, because the domain being language, that imposes a fully connected graph, because all the words in our sentence are working together, right? Okay, so to do that, we just use, we just remove the constraints of the neighborhood. And then the second part is changing the aggregation functions. So we've seen that before as aggregation functions, we were using sums or maxes and stuff like that. We need to use softmax here because softmax is the one that is using in transformers. Okay, so just to recap, what we've seen today is the transformers architecture and how transformers can be seen as GNNs. And if you don't have any more questions, I thank you for your attention. Okay.